The night sky, vast and serene, hides a lurking danger. Hurtling through the darkness are countless asteroids and comets, some large enough to obliterate entire cities. Humanity has long feared these celestial wanderers, once seen as harbingers of doom. Today, the threat isn't myth, it's real. Between the stars and shadows lies a chaotic realm where rocks the size of mountains travel in silent orbits, unnoticed by most. For centuries, meteors and asteroids were objects of fear and wonder, their fiery descent inspiring legends of disaster. But in our modern age, they represent a very real danger, a danger that humanity has only just begun to confront. With powerful telescopes, cutting-edge space probes, and coordinated global efforts, we're racing to monitor these near-Earth objects, uncovering their secrets and preparing for the unthinkable. Because out there, in the cold vacuum of space, the cosmos doesn't play favorites. It can gift life as easily as it can take it away. In recent years, NASA carried out a bold experiment to see if a spacecraft could shift an asteroid's path, testing the feasibility of an actual planetary defense. The selected asteroid posed no direct danger to us. Scientists chose it because its size resembled those that could, in theory, threaten Earth. A collision was arranged, small craft versus cosmic rock racing at extraordinary speed, and cameras tracked every second. Although this test mission succeeded in altering the orbit, it left behind a spiral of debris, spurring new questions about what truly happens when humanity attempts to bend the cosmos to its will. A second mission is now on its way to scrutinize the aftermath. It departed aboard a rocket not long ago, bound for a multi-year journey. Engineers speak of it as a crash scene investigation, hoping to determine whether that initial strike merely gouged a crater or upended the asteroid entirely. 2 compact companions will be released upon arrival to map the interior and analyze any lingering changes in the rock's structure. This operation marks one of the most decisive steps ever taken to understand not just how to steer an asteroid, but how to do so without creating an even bigger threat. It is a cautious dance, part scientific inquiry, part practice for a future we hope never comes. There is a growing network of observatories around the world, many of which are funded to search for near-Earth objects. Whenever an unknown visitor makes its presence known, that discovery triggers a flurry of calculations to determine how close it might come in the weeks, months, or years ahead. Most of these findings are quietly posted in open databases, listing the date of a flyby, approximate size, and distance at closest approach. People rarely notice when an asteroid sails by at a distance a few times greater than the Moon. And yet, astronomers keep a watchful eye on every close pass, fully aware that the difference between a harmless near miss and a catastrophe is measured in mere fractions of cosmic space. Larger asteroids capture our imagination and stoke our fears. From time to time, it is announced that an object the size of a skyscraper will skim past Earth. The distance may be considered safe by scientific standards, but the notion that a chunk of rock hundreds of meters across is cruising within a span easily measured in mere lunar distances has a sobering effect. Such objects, if unaccounted for, would be capable of devastating a city or an entire region. Past strikes have permanently scarred our planet, leaving massive craters as monuments to an ancient violence that shaped our evolution. Much of Earth's history has been punctuated by these collisions. Entire species have been wiped out, while others have risen to fill the void. Subscribe to Frontiers of Infinity to explore more mysteries like this, because the universe is bigger than we can imagine. Over time, NASA and various agencies have catalogued thousands of near-Earth objects, but many more remain undiscovered or insufficiently tracked. Half of the smaller space rocks that pass near us are often found only after they have moved away. Although developments in ground-based telescopes and infrared sensors have significantly improved detection rates, the skies remain vast, and even the sharpest eyes can overlook fragments that arrive at awkward angles or blend in with the background of stars. A single untracked visitor could change the course of human history. That possibility has led to an array of theoretical strategies for averting a potential collision. One method suggests hovering a gravity tractor spacecraft near the rock for years, gradually shifting its course without causing fragments to scatter. Another proposes altering its surface properties, painting it, in a sense, to make the asteroid reflect more or less sunlight, thus taking advantage of subtle radiation pressure. More drastic ideas involve using nuclear explosives to divert or fragment the threat, though that scenario poses the risk of turning one large threat into a swarm of smaller ones. Of all these ideas, only a direct impact has been tested, at least in a limited form. The results showed that we can indeed knock an asteroid off its path, but the debris plume that arose gave everyone pause. Over 2 million pounds of rocky fragments were tossed out into space. Some scientists predict that bits of this debris may eventually wander near our atmosphere or that of Mars in the coming decades, igniting tiny flashes of light as they burn up. The thought of a man-made meteor shower is thrilling and unsettling all at once, hinting that our presence in the solar system is no longer passive. If these fragments do become visible, they will draw renewed curiosity toward the power we hold, and the power that remains beyond our control. This experiment also serves as a reminder that whenever we engage in planetary defense, we must be prepared for complexities no simulation can fully anticipate. In many ways, the rocky bodies near us are still poorly understood. Some are solid stone, while others are loosely bound collections of rubble or dust. A strong impact against one might transfer momentum cleanly, but against another, it might disintegrate the surface layers, spreading chunks in all directions. These differences matter when the goal is to protect Earth, rather than unleash further chaos. In the coming months and years, there will be close approaches from asteroids both large and small. Some will pass within just a few lunar distances, enough to rank as potentially hazardous. To the scientific community, that is not necessarily a sign of imminent doom, but rather a reminder that vigilance must be constant. Our planet moves through a cosmic shooting gallery, and only sustained observation can give us a meaningful chance to intervene if an object ever lines up on a collision course. For many viewers, the sheer magnitude of the universe can feel overwhelming. But the deeper we look, the more we find ourselves captivated by the delicate interplay of gravitational forces that thread our solar system together. These asteroids serve as time capsules of the early days of planetary formation. Some might still bear traces of the organic materials that seeded our world with the ingredients for life. Others might one day become stepping stones for mining ventures or exploration missions. We stand at a crossroads between harnessing these primordial relics and defending ourselves from their destructive potential. It can be difficult to imagine how a chunk of rock, silent and drifting through space, might reshape life on Earth in a single day. But we only need glance at the geological record to see how swiftly everything can change. Countless species vanished in cataclysmic events triggered by massive impacts, including one that spelled the end for the dinosaurs. While we do not face an immediate threat on that scale, the lesson is that cosmic events unfold on their own timetable, not ours. In the face of this, our greatest tool is knowledge. There is a quiet comfort in knowing that scientists worldwide refuse to turn away from the possibility of future impacts. Observatories on every continent track the heavens each night, uploading data and cross-referencing orbits with cutting-edge algorithms. International collaborations share results and refine calculations to predict an asteroid's path for decades to come. With each piece of data, we gain a bit more reassurance, or occasionally a new cause for concern. For that reason, some voices urge for more robust funding and more capable detection systems. They point out that time is our biggest ally, and the sooner we detect a threat, the easier it is to deflect. There are, of course, those who find the idea of a looming cosmic danger both exhilarating and terrifying. This tension resonates through the stories we tell, from science fiction epics to the news that flashes across our feeds whenever an asteroid's approach makes headlines. Perhaps that very blend of fascination and dread is what keeps humanity alert. After all, the question of our cosmic vulnerability has long fascinated us. We have only to look up on a clear night and marvel at the countless paths that cross the deep sky, each representing an object following the timeless pull of gravity. If you find yourself stirred by these possibilities, be assured that there is more to discover. The greatest journey is just beginning, as we learn how to coexist with these wandering giants and, when necessary, guide them away from a collision with our fragile planet. You might feel drawn to watch for updates whenever an observatory reports a significant approach, or to dive deeper into the mechanics of space missions aimed at safeguarding our world. Even if the odds of a major impact in our lifetimes remain small, the potential stakes could not be higher. At times, one cannot help but wonder if these efforts mark the start of a grander era, in which humanity takes a more active role in shaping its fate beyond Earth. Each new probe that leaves our atmosphere reveals some hidden corner of our solar system, illuminating the frontier of what is possible. Knowing that we are capable of influencing the trajectory of an entire asteroid is both thrilling and humbling. The energy involved in such maneuvers is mind-boggling, yet nature's scale dwarfs our attempts with ease. A spacecraft might alter a rock by a fraction of its speed, but one random gravitational nudge delivered by a passing planet or another asteroid could unravel the best-laid plans in a heartbeat. Perhaps our ability to endure will hinge on our readiness for the unexpected. A day may come when detection systems pick up a genuine threat, and we have only a handful of years to muster an international response. Missions similar to the ones recently tested and launched could stand as the only line of defense. The notion of the entire world uniting under a single cause, preventing a cosmic catastrophe, might sound like a page out of fiction, yet the seeds of that cooperation are already planted. We see them in data-sharing agreements, joint ventures between agencies, and the continuing development of powerful sky surveys. It is often said that we live in the golden age of astronomy, with advanced telescopes capturing images of galaxies billions of light-years away. Yet for all that distant beauty, there is a pressing need to focus on the threats in our cosmic backyard. The group of asteroids passing within a few lunar distances in the next couple of years will likely prove harmless, but each pass is a reminder that Earth is just one more body spinning in the dark. There is no cosmic shield to keep these objects away, only our wits and the modest tools we have begun to forge. The mere existence of these attempts, collisions carried out by spacecraft, follow-up missions to analyze the results, signals a shift in how we perceive our place in the solar system. We have always been explorers at heart, but now we are also guardians, mindful of the hazards that lurk in the spaces between planets. That shift in perspective brings with it a sense of responsibility. We are no longer spectators. Whether we act out of self-preservation or scientific pursuit, we have begun to claim a role in the cosmic drama, for better or worse. In the grand scheme of things, asteroids are ancient rubble, relics of the solar system's formation. They come in all shapes and compositions, from dense metal cores to loose clusters of gravel barely holding themselves together. Some may have delivered water and organic molecules to an infant Earth, helping life to blossom here. Others could end that same life in an instant, if fate and timing conspire to hurl them our way. In this duality lies the awe they command. They are both creators and destroyers, weaving themselves into the ongoing story of our planet's evolution. The first mission that deliberately nudged an asteroid has only just begun to reveal its long-term consequences. Data continues to pour in, revealing exactly how much the orbit shifted and how the asteroid's structure changed. Even as researchers digest those insights, they wait for the next expedition to arrive years from now, certain that the story will grow more complex once direct observations reveal every detail of that crater and the debris field beyond. If those fragments do reach Earth's atmosphere, they might create a faint glow in the night sky, human fingerprints on the cosmos, so to speak. We have only scratched the surface of what can be learned from such feats. As missions become increasingly ambitious, we might discover that some methods of impact or deflection are more effective than others, depending on an asteroid's composition. What works for a relatively compact rock might fail spectacularly against a rubble pile asteroid. And if in the far future we do face a genuine threat, the difference between success and calamity could hinge on these incremental steps of knowledge being gained right now. If you find yourself gripped by a quiet sense of urgency or a spark of curiosity, hold on to it. The cosmos has a way of reminding us that we are part of a much larger tapestry. We have access to data, simulations, and international collaborations that span the globe. We can run scenarios on supercomputers and build probes to gather first-hand evidence. Yet, in the hush of a star-filled night, it remains humbling to realize that a single stray asteroid has the power to reset life as we know it. The idea of redirecting cosmic wanderers might have sounded like pure fantasy only a generation ago. Today, it stands as an emerging discipline at the intersection of astronomy and engineering. This discipline demands both caution and boldness. Caution to anticipate every unintended side effect. Boldness to face a phenomenon beyond any we have truly mastered. As new space missions launch, as advanced telescopes scan the sky, we drift steadily from speculation into the realm of practical readiness. This quiet revolution could mark a defining chapter in humanity's story, one in which our impulse to explore turns towards safeguarding the only home we have. Subtle or not, the call here is to remain watchful, to stay informed, and to reflect on the magnitude of the challenges that asteroids represent. If our ancestors reacted with superstition and dread when they saw fireballs streak across the heavens, we now respond with reasoned vigilance, a vigilant wonder that might unite us in a cause that transcends borders and ideologies. Whether you feel awe or apprehension, this is the time to stay curious, to follow the developments in planetary defense and exploration, and to contemplate how human ingenuity might one day protect our fragile blue sphere from the ancient rubble circling the sun. It is humbling to know that despite all our advances, we are still subject to cosmic whims. Yet within that humility lies a resolve to probe deeper, question further, and challenge the boundaries of what we can achieve. A single spacecraft has already changed the orbit of a small asteroid. Another probe is on its way to examine that event's hidden details. Day by day, we grow less passive in the face of cosmic forces and become more like participants in an endless dance, threading our paths through an ocean of drifting stones. And though we may never gain complete mastery over these celestial wanderers, our determination to understand and prepare might ensure that if one day the Earth stands in harm's way, we will have a plan, one forged through curiosity and vigilance, tested in the darkness that surrounds us. In the wake of that first deliberate collision with an asteroid, scientists have begun analyzing the deeper implications of what it means to alter a celestial body's path. The mission that successfully nudged a small rock was championed as a pivotal step toward true planetary defense. Yet in the aftermath, it became clear that the result was more complex than a straightforward bump. Instruments detected a vast cloud of rocky fragments streaming away, like a cosmic plume stretching for thousands of miles. Those who tracked this lingering debris wondered whether small grains might eventually drift into Earth's vicinity, or even reach other planets in the years ahead. While the possibility of man-made meteor streaks filling the sky remains uncertain, it underscores how little we have yet to learn about orchestrating large-scale interactions in space. The entire affair sparked renewed focus on how we might respond if a larger object threatened Earth. Space agency officials praised the outcome as a promising display of our capabilities, but they also acknowledged that the approach needs much more refinement. One can imagine a scenario in which an impact intended to deflect an asteroid inadvertently scatters chunks that still cross our planet's path. A single mission cannot be the final answer to such a peril. It is a first clue, a foothold in a dizzying climb toward genuine control over our cosmic surroundings. Because of this, a follow-up probe was sent to chart the effects of the collision in unprecedented detail. The craft left Earth recently, traveling aboard a trusted rocket, and it carries not just cameras, but specialized radar instruments. Its twin companions, designed to be released as small hitchhikers, will circle the asteroid system from close range once they arrive. Their instruments can peer beneath the surface, scanning for signs of internal fracturing or large voids. If the test collision shifted the asteroid's internal alignment or changed its density distribution, that could alter how momentum transfers when a bigger strike occurs in the future. Engineers believe this information is priceless, since the next time a real threat appears, decisions may hinge on whether a spacecraft needs to bump a firm object or carefully redirect a loose pile of rubble. These endeavors are part of a broader shift in how we engage with the solar system. Once, our best approach to asteroids was limited to distant observations through telescopes. Now, we move boldly toward them with robotic explorers, even crashing intentionally to see what happens. Some might say it feels a bit like cosmic archaeology, mixed with high-stakes hazard training. It is a fine balance between exploration and defense, curiosity and caution. Yet as technology advances, so does the ambition behind these missions. There are already plans for increasingly complex rendezvous with other asteroids, missions that may even attempt sample returns or small landers aiming to dig deep into the regolith. At the same time, the skies around Earth remain busy. Scouts and instruments across the globe watch for newly discovered near-Earth objects, logging details about each. Many appear on the radar briefly and vanish back into the dark with no threat implied. Others loop around periodically, reminding us that they will be back, possibly closer next time. The sense that our planet is adrift in a cosmic shooting gallery often sparks philosophical musings. Do we see ourselves as guardians of Earth, or as tenuous participants in a larger cosmic narrative? Either viewpoint leads to a recognition that our vigilance cannot waver. It is in this atmosphere of both cautious relief and renewed urgency that individuals worldwide wait to see what the newly launched probe will find when it reaches its destination in a few years. The images from the first collision were dramatic, a spacecraft accelerating toward its target until the final moments of contact, followed by a sudden cutoff and a growing plume observed from afar. This time, researchers want to map every scar in crisp detail. Perhaps the object bears only a fresh crater, or perhaps it has been deformed in ways no one expected. Some scientists expect to see changes in the orbited rock's spin rate, or even a loosening of surface material that slid toward a newly exposed region. If the body is a rubble pile, that top layer could have rearranged itself significantly, with boulders shifting places and fractures slicing the interior. Subscribe to Frontiers of Infinity to explore more mysteries like this, because the universe is bigger than we can imagine. In the bigger picture, all of this exploration dovetails with the ongoing survey of objects that periodically swing by Earth. Over the next few years, watchers anticipate multiple asteroids passing within a handful of lunar distances. Some are no bigger than small buildings, barely large enough to cause localized harm if they were to enter our atmosphere. Others are more massive, capable of leveling entire cities if they struck land. Official alerts about these objects typically emphasize that no impact is expected, but the repeated mention of closest approach can stir unease. People sometimes envision a scenario in which one of these asteroids appears out of nowhere, with little time left to act. In reality, the best defense is early detection, giving ample lead time for launching a deflection mission. The first test collision has shown the method can work, but only if we have enough warning to mount and carry out such an operation. This emphasis on timing is why many experts call for more advanced space-based telescopes designed specifically to spot and track near-Earth objects. While ground-based observatories cover large portions of the sky, they face limitations of weather and daylight. A satellite peering outward from a solar orbit or from a vantage point near Earth could detect faint objects more consistently. The earlier we notice an approaching threat, the more modest a nudge it might need to be safely redirected. Miss that window, and the required intervention grows riskier, potentially involving more force and more complicated outcomes. Public awareness around these issues has grown in recent years, thanks to news coverage and even dramatized accounts in popular culture. Yet, for every near miss that captures headlines, there are many more that pass unnoticed outside the scientific community. Sometimes the world only hears of a close approach after it has already happened, stirring confusion and alarm when it appears that astronomers made a late discovery. In truth, near misses occur fairly often at smaller scales. Earth's atmosphere even encounters small objects weekly, which burn up harmlessly. The difference lies in the size of the visitor and its potential to cause damage on the ground. Experts sometimes remind us that while certain asteroids come within millions of miles, that distance is still enormous in human terms. But cosmic terms operate on a scale that makes a few lunar distances uncomfortably tight. One might hear that an asteroid will miss Earth by a margin of only 3 times the distance to the Moon and think that we narrowly averted a crisis. Another might shrug and point out that such a margin is still hundreds of thousands of miles. Both perspectives are correct, highlighting just how relative our sense of danger becomes in the domain of orbital mechanics. Against this backdrop, missions like the latest asteroid reconnaissance stand out as crucial. By investigating how much an asteroid's spin, shape, or orbit changed, these spacecraft build a playbook for future interventions. They will likely gather data on the texture of the surface, the composition of subsurface layers, and the precise distribution of ejected debris. Each of those pieces adds a new line of knowledge, showing whether a single impact might suffice under various conditions or if multiple collisions would be required. Some have even proposed using smaller spacecraft to encircle an asteroid in advance, blasting it from different angles to shepherd it onto a safer path. Though that remains theoretical, it underscores just how creative planetary defense concepts can be. There is also an eerie allure in the idea that a human-made cloud of dust or rubble could become a roaming feature in the solar system. Perhaps in a distant decade, a faint meteor shower in our skies will be traced back to fragments left by that first collision experiment. If so, it will mark one of the first instances in which humanity has left not just footprints on the Moon or rovers on Mars, but particulate signatures drifting among the planets. This new layer of cosmic dust would be a testament to our ongoing transition from passive observers of the heavens to participants who, for better or worse, alter the environment beyond Earth. In an age dominated by quick news cycles and fleeting online trends, it is remarkable that the topic of asteroid defense has maintained a steady presence. Part of it may be primal fear. People are drawn to stories about potential cataclysms. Another part lies in genuine scientific curiosity. These are ancient objects, older than any life on Earth, and studying them can rewrite entire chapters of our understanding about how the solar system formed. That same knowledge can keep us safe. If a day comes when a newly found asteroid has even a small chance of colliding with Earth within a decade or two, public interest will likely surge far beyond current levels. The groundwork laid now could prove vital to responding effectively, should that moment of crisis arise. Even on a purely existential level, the effort to track and prepare for asteroid threats highlights a rare unity of purpose. Researchers in different countries, under different agencies, share data and expertise. Missions are frequently collaborative ventures, with hardware built in multiple locations, launched by different rockets, and guided by teams spread worldwide. It is a reminder that the cosmos does not recognize our borders or conflicts, and a large enough object could spell doom for everyone equally. Planetary defense, as a result, has the potential to foster cooperation that transcends usual dividing lines. That alone might be worth celebrating, though it springs from the recognition that our planet is fragile. For now, we await results from these new missions with a mixture of anticipation and cautious optimism. If the data confirms that an asteroid can be altered without creating too much collateral debris, then that becomes a powerful reassurance. If the findings reveal previously unknown complications, we learn from them and refine our strategies. In either case, there is no turning back from the prospect of planetary defense. The genie is out of the bottle, so to speak, and with each successful demonstration, the method becomes more mainstream. Meanwhile, small public calls to action might be worth considering. The concept of citizen science has already transformed other fields by enlisting volunteers to help classify galaxies or spot changes in climate data. In the realm of near-Earth objects, individuals with quality telescopes can participate in tracking and confirming observations, sending their findings to clearinghouses that integrate these measurements. Such community involvement broadens the search net, bringing more eyes to the sky. This also cultivates a sense of shared responsibility for the defense of our world. Little by little, the narrative evolves from scattered research initiatives to a unified global vigilance. Some might say this is exactly how humanity matures as a spacefaring civilization. First, we discover potential hazards. Then we plan how to mitigate them. Along the way, we discover new scientific horizons, unravel mysteries about how water or organic compounds might have arrived on Earth, and deepen our grasp of orbital mechanics. The impetus for such knowledge is partly rooted in self-preservation, but the revelations gained can ripple through other domains of space exploration. When the probe finally reaches its destination to examine the remains of that collision, a careful choreography of maneuvers will begin. Controllers back on Earth will guide it in ever closer orbits, building a three-dimensional map of the surface. The small companions will deploy, possibly drifting near the crater to gather high-resolution scans. In the event that the asteroid's motion was radically changed, the probe might capture new vantage points that reveal how the moonlet orbits its larger companion. Observations of temperature variations will shed light on whether newly exposed layers of rock behave differently when bathed in direct sunlight. And if the mission manages a flyby so close that it risks impacting the surface, scientists may get the clearest images yet of the cosmic wound left by humankind's experiment. Some might feel that this is a prologue to more direct interventions, or that in a century's time we will be adept at corralling asteroids for resources as well as for protection. Others may worry that poking these ancient wanderers is playing with fire, risking unforeseen events that could bring unintended harm. Regardless of which perspective one holds, the next few years promise answers to some crucial questions. Does deflection work as neatly in practice as it does in theory? Can we refine and scale up the method if a bigger object looms on the horizon? And can international cooperation remain robust if the threat demands swift, decisive action? Those questions mirror the gravity of our relationship with the cosmos. We are a tiny civilization on a fragile world, trying to harness knowledge that might prevent a world-altering impact. By doing so, we take one step deeper into a realm once reserved for fiction. The rocket carrying the probe out of Earth's atmosphere might as well be carrying the weight of that question. After all, it is not simply investigating the aftermath of one test. It is gathering insights that could decide our collective fate at some unforeseen hour. For the moment, that hour may feel distant. Headlines come and go, with many people scarcely aware that a second spacecraft is already en route to that distant pair of asteroids. But a few keep careful track of every milestone, celebrating each successful course correction or instrument test. They see in these missions the seeds of a future in which humanity no longer waits helplessly for the random impact of a cosmic bullet. Whether that future arrives soon or remains far off, the sheer fact that we have begun to nudge asteroids at all is enough to signal that our role in the solar system is evolving. In the quiet intervals before the next big discovery or dramatic news alert, one can reflect on how fragile this process is. We rely on an unbroken chain of technology, from launch platforms to communications relays to mission control, to pull off feats that until recently were deemed nearly impossible. One malfunction, one oversight, and the entire mission could fail. Yet somehow, despite the odds, spacecraft continue to slip past the boundaries of our world, carrying cameras, instruments, and instructions from Earth. Most of the time, they succeed in at least some part of their objectives, returning images that expand our sense of wonder and data that sharpen our strategies. One day, the threat might not be hypothetical. an object of considerable size could appear on the horizon, discovered on a path that intersects with Earth's orbit. The clock would start ticking, and the knowledge we have gleaned from these earlier ventures would become the blueprint for our response. We might attempt a gravitational tug, a direct collision, or a combination of measures. Global leaders would wrestle with timelines, budgets, and public fear. Scientists would scramble to finalize calculations about how best to minimize debris. If done correctly, we might see the asteroid's course shift, leaving Earth unscathed. If done poorly, well, history reminds us that cosmic impacts can drastically reshape the surface of our planet and the arc of life itself. For now, we stand in the calm before such a storm, practicing, rehearsing, and examining each outcome. The second craft heading to that stricken rock is set to arrive in a time frame that sounds both distant and immediate, depending on one's perspective. Years may feel short in the cosmic sense, yet they are long enough for entire breakthroughs to happen in earthly labs. By the time it closes in on its target, we may already have new revelations about other asteroids or fresh near misses to discuss. And if by some chance an urgent threat emerges before then, we may have to act with partial knowledge, hoping the blueprint from the first collision mission is enough. Through it all, a delicate thread of tension runs. We are both explorers reaching for answers about our place in the universe and defenders preparing for a blow that might or might not come in our time. That tension is not something to fear, but to heed. It reminds us of the stakes. Our endeavors in space are no mere pastime. They can be the difference between flourishing on Earth for millennia to come or witnessing a tragic turn that might have been prevented if only we had moved quickly enough. Meanwhile, the larger asteroids that approach Earth in the near future offer practice runs in observation and modeling. We monitor their trajectories, measure their reflective properties, and refine the data in real time. If they pass by safely, we chalk it up as another narrowly avoided cosmic handshake. If something shifts and the risk grows, well, we already have a precedent. We know that a small spacecraft, if deployed with care, can impart a measurable push. We still have to perfect the rest of the equation, ensuring that any debris trail does not backfire, that we understand how each asteroid structure responds, and that we can cooperate as a global community to mount the mission in time. These days, the solar system reveals itself as both a museum of ancient rocks and a crucible for new technological leaps. Some asteroids might one day yield minerals, water for propellant, or stepping stones for human crews venturing deeper into space. Others might loom as threats requiring swift, expertly coordinated maneuvers. There is a poetry to the idea that the same class of objects that once seeded Earth with life-giving essentials could, under other circumstances, extinguish that life altogether. Through the tinted lens of caution, each close approach becomes a lesson, each mission a chapter in a growing manual on cosmic stewardship. We learn that deflecting a rock is possible, but complicated. We learn that even a short mission can reshape an asteroid in ways we did not predict. And we come to see that knowledge in this field is a constantly evolving tapestry woven from countless observations, simulations, and bold flights into the unknown. If each new revelation warns us of the difficulty ahead, it also kindles hope that we can adapt, innovate, and stand ready for whatever the sky sends our way. In a world where satellites hover in low Earth orbit and new rockets launch almost every month, it is easy to forget how vulnerable we remain to the celestial debris roaming beyond our planet's immediate neighborhood. The same society that once feared comets as prophecies of doom now sends probes to survey asteroids with an air of both excitement and caution. But beneath the thrill of exploration, there lingers a recognition that some events in space are not mere curiosities. One day, they might force us to look survival in the eye. Among those who keep daily watch, discussions center on the scale and composition of asteroids that approach within a few lunar distances. The difference between a small, tumbling fragment and a 1,000-foot wide mass is not just a matter of size. It is a question of what methods might succeed if we need to divert such an object in a hurry. Small fragments may be nudged aside more easily, but there is also the risk of them breaking into multiple pieces if struck too hard. Conversely, larger asteroids demand more energy to steer, yet might stay more intact after a collision. Scientists refine these notions by examining images, radar returns, and spectroscopic data that hint at whether a rock is metallic, rocky, or a loose amalgamation of dust and stone. All this effort feeds into tables and charts that mission planners study when conceptualizing how to mount a rapid response. Would a single impact suffice, or would multiple vehicles be needed? Could a simple change in the rock's reflective properties alter its path given enough time, or would we need to rely on more extreme measures? Each approach entails different risks. Detonating an explosive near an asteroid might impart momentum, but it could also send shards spiraling in unpredictable directions. Using a soft push that spans months or years requires we detect the threat early. A single discovery made too close to the predicted impact date might render the gentler methods ineffective. Time is often our greatest asset, and the race to improve detection capabilities reflects a shared desire not to be caught unprepared. Public fascination with all this can be seen in how readily people ask about upcoming near misses, particularly those labeled as potentially hazardous. The term may sound alarmist, but it only signifies that an object meets certain criteria for its orbit and size. Most such asteroids still pose no direct threat. That said, each new close pass sparks discussions about how narrow the margin might be next time. If an orbit shifts slightly due to a planetary encounter or other gravitational effects, an asteroid that was harmless for decades can suddenly become a candidate for serious study. One tiny nudge in the vacuum of space can make the difference between a harmless flyby and an eventual collision. Sometimes smaller asteroids drift by unnoticed, only for astronomers to discover them once they have passed Earth. This typically garners little attention in news headlines, yet it illustrates how formidable a task it is to keep track of all cosmic wanderers. There are initiatives aiming to reduce these blind spots, including surveys equipped with telescopes capable of scanning large swathes of sky more frequently. Plans are underway to place new detectors in space, specialized for spotting faint objects that might be lost against the bright backdrop of the Sun if viewed from Earth. Each advance in detection is a stride toward a future where few surprises slip past our planetary defenses. Even with improved technology, uncertain variables persist. Not all asteroids have stable, well-known paths. Some are influenced by thermal emissions, a phenomenon where an asteroid absorbs sunlight and re-emits that energy as heat. Over time, this can subtly alter its trajectory, a factor known as the Yarkovsky effect. Large bodies experience this to a lesser degree, but smaller, more irregularly shaped asteroids can see their courses shifted enough to complicate predictions. While this effect has been measured for certain near-Earth objects, many remain poorly understood in that regard. It is one reason why continuous observation is necessary, rather than relying on a single snapshot of their orbit. The broader public tends to learn about these nuances in waves, usually following a headline-making event or a close approach that becomes a media talking point. Some find the topic nerve-wracking, whereas others find it thrilling. In either case, awareness grows. Educational programs have begun highlighting asteroid science, and some observatories invite the public to see firsthand how detections occur. Enthusiasts may learn how to read orbital elements, interpret approach distances, and understand why a small variation in velocity can translate into tens of thousands of miles over time. This kind of outreach reminds us that cosmic hazards do not have to be relegated to the realm of paranoia. They can be approached with understanding and readiness. Subscribe to Frontiers of Infinity to explore more mysteries like this, because the universe is bigger than we can imagine. As the years roll on, the probes designed to investigate the aftermath of the first asteroid collision mission serve as a beacon of progress. Engineers celebrate each milestone, such as a crucial course correction performed billions of miles away, or the successful activation of instruments once the craft nears its target. In these moments, a hum of excitement reverberates through the planetary defense community. They see these missions as more than just academic exercises. They are rehearsals for preventing disaster. Data gleaned from them shapes future mission proposals and helps agencies justify larger budgets, arguing that prevention is far cheaper than mitigation after impact. Several agencies keep a public catalogue of near-Earth objects that extends well into future decades. For each listed asteroid, they include probabilities of collision, which in most cases remain extremely low, on the order of fractions of a percent. Yet when an object stands out with a higher probability, even if it is still small, the community takes notice. Astronomers scramble to gather additional observations, refining orbital calculations until the risk is either confirmed or dismissed. This repeated cycle of new threat discovered, calculations made, threat downgraded, often unfolds behind the scenes, invisible to most of the world. Sometimes the media picks it up, leading to sensational headlines that fade away once updated data shows no real hazard. Still, that routine is part of what keeps the entire system honed for the day when a genuine threat persists under repeated observation. Those who look deeper into the history of asteroid impacts find no shortage of dramatic examples. The crater in the Yucatan Peninsula stands as the most famous, linked to an event that helped end the reign of the dinosaurs. Much smaller but more recent events, such as the one that leveled a forest region a little over a century ago, demonstrate that not all impacts must be gigantic to cause substantial damage. And even within recorded history, meteor sightings have rattled towns and sparked widespread awe when fireballs streak across the horizon. The scale of cosmic forces can be staggering, regardless of whether they arrive on a cataclysmic or modest scale. Yet this is not solely a tale of looming catastrophe. Many asteroids carry potential gifts. Some contain water, precious metals, or rare minerals. Plans exist to one day harness these resources, potentially fueling future missions or establishing off-world manufacturing. These same rock formations that could destroy life if they strike Earth might, in another scenario, enable advanced exploration or economic leaps if approached safely. It is a curious twist that the objects posing one of our greatest existential threats could also become stepping stones for humanity's expansion into space. Such is the paradox of the asteroid world. Both menace and opportunity bound into silent chunks drifting through cosmic darkness. It fits our nature, perhaps, that while we scramble to guard against them, we also dream of harnessing their abundance. In the coming decades, some of the knowledge gleaned from deflection research might be turned toward capturing small asteroids in stable orbits around the Moon, where they could be mined. The ethics of such manipulation remain a subject of debate. Should we, in our rush to exploit space, risk altering orbits that have existed for billions of years? What if an operation goes awry and sends a rock hurtling toward Earth unintentionally? These questions illustrate how planetary defense and resource acquisition sit at opposite ends of a shared spectrum of asteroid interaction. Of course, these future possibilities hinge on the data being gathered now. If the probes examining the aftermath of that first collision find that shifting an asteroid's orbit is easier or harder than expected, that intelligence trickles into the broader discussion. Every detail about mass distribution, internal voids, or unexpected ejector patterns helps refine the blueprint. On a philosophical level, it is remarkable how a single experiment, lasting mere seconds in terms of the actual collision, can have a ripple effect across decades of strategic planning. Humanity's story of navigating asteroid threats is still in its opening chapters, and each mission adds a new thread to that tapestry. As more telescopes come online, the volume of discovered near-Earth objects is likely to surge. Each will get a preliminary orbit calculation, and a handful may raise eyebrows. Sometimes, you might see speculation about whether our detection rates are outpacing our ability to respond if something truly dangerous appears. The world's capability to launch a deflection mission on short notice remains untested, particularly if we are dealing with an asteroid that offers only a few years of warning. While initial collisions have shown that we can move a rock's orbit, the practicality of doing so quickly for a large threat is still uncertain. That uncertainty drives persistent calls for increased funding, better infrastructure, and a well-defined international framework that outlines how to respond if an emergency emerges. Occasionally, there will be talk of a new asteroid passing by at an uncomfortably close range. Reports mention it could come within 1 million kilometers, or about 3 times the distance of the Moon, which for an astronomer might be considered a near miss, but for a layperson sounds inconceivably distant. Both perspectives have validity. On the cosmic scale, that is indeed a hair's breadth. On the human scale, it remains vast. Yet repeated enough, these passes have a way of normalizing the idea that cosmic objects do come close, and that Earth does not stand apart from the random flux of space. Over the millennia, countless chunks have impacted this planet, reshaping climates and ecosystems. The difference now is that we have the means to see them coming and possibly push them away. This sense of readiness does not necessarily negate the awe. A sky filled with glittering stars and the occasional meteor trail can still provoke a deep sense of wonder. Behind that wonder, though, is a mounting comprehension of just how dynamic our solar system remains. The orbits we rely on for navigational charts or for sending spacecraft are part of a grand dance that also involves uncharted debris, some of which we have yet to discover. The best approach to living in a cosmic shooting gallery is to appreciate its beauty while taking every precaution we can. In the near future, there will be more missions devoted to not only observing, but interacting with asteroids and possibly comets. Some might test new propulsion systems capable of long-duration station keeping near a target. Others might land on particularly intriguing specimens, drilling into subsurface layers to retrieve pristine samples. Each mission carries dual importance: scientific exploration on one side, planetary defense capabilities on the other. Perhaps we will see the day when a gravity tractor demonstration is carried out, where a spacecraft sits close to a small asteroid for months, gently shifting its orbit using the subtle pull of gravity. If successful, it would confirm yet another method by which Earth could be safeguarded, assuming enough time remains to execute it. Returning to the question of how we respond as a global community, the blueprint for international collaboration is starting to take form. Conferences and committees bring together experts from around the world, creating contingency plans and communication protocols. If a threat emerges, which agency declares it? How do nations share data effectively and avoid panic? Who coordinates the launch of any deflection effort, and which countries supply the rockets or the spacecraft? These are complex issues, but stepping stones have been laid in the form of shared missions, funding agreements, and open data policies. Such cooperation may be tested if an actual crisis looms. The tension between national interests and global survival can be stark. Yet it could also serve as a powerful catalyst for unity. In historical moments of genuine peril, humans have sometimes banded together despite ideological divides, though not always successfully. Asteroid defense might prove a scenario that compels unprecedented collaboration, given that no region on Earth would be spared by a large impact. Knowing that, one can remain cautiously optimistic that the right systems are being built now, even if they remain nascent. For any individual hoping to follow these developments, resources abound. Public websites track known near-Earth objects, listing each approach date alongside its size and distance. Some scientific papers go deeper, discussing the composition of select asteroids, possible mining prospects, or the mechanics of orbital deflection. Amateur astronomers gather on forums to exchange findings and occasionally capture images of fast-moving targets against the starry backdrop. In these ways, the conversation becomes broader than academic circles, permeating the ranks of hobbyists and enthusiastic citizens. Their passion adds another layer of scrutiny, ensuring that if a curious blip appears in telescope data, someone might notice and raise the alarm. Within this collective endeavor, the newly launched probe heading out to survey the aftermath of the first collision carries a special weight. It stands as proof that we are taking the matter seriously, that we want to know every facet of a deflected asteroid's behavior. Will the body remain stable, or will it shed fragments that could wander off unpredictably? Are certain internal structures more likely to produce dangerous byproducts if impacted a second time? Such insights will help shape future mission profiles, ensuring that if an emergency arises, we do not compound the threat by inadvertently shattering a large body into multiple smaller but still hazardous fragments. It is a delicate balance. The same force that can save us from one large threat might scatter it into many smaller ones, each now on a slightly varied path. One can almost picture a map of near-Earth space dotted with potential fallout trajectories. It is not enough to impart a push. We must plan for what that push does to the entire mass. The phrase planetary defense may evoke images of grand technology, but in practice it is about intricate physics, fine measurements, and collaborative consensus. Every step, from the design of the spacecraft to the calculations of the asteroid's spin, must be precise. Although these missions can seem far removed from daily life on Earth, the stakes become painfully clear when we consider history's examples of devastating impacts. The memory of cities awakened by explosive fireballs or entire species vanishing after colossal collisions is woven into our planet's geological and evolutionary record. There is no rule saying it could not happen again. The difference now is that our species has knowledge and perhaps the will to tip the odds in our favor. As we learn more about how to accomplish this, conversations inevitably turn to the philosophical dimension. Are we interfering in cosmic processes that should remain untouched? Or is the drive to protect life a natural extension of our obligation as a conscious, capable civilization? Such debates, while abstract, shape public perception and policy direction. They remind us that planetary defense is not merely a technical puzzle, it is also a moral undertaking. Yet many argue that if a threat can be averted without harming other worlds or life forms, then it stands to reason that we should act. What emerges from all these threads, a test collision, a follow-up mission, ongoing surveys, is a sense that humanity is gradually learning to guard its home. The next big milestone might be the moment the new probe completes its 2-year journey and transmits its initial close-up images of the impact zone. Even the most jaded observer might pause to see what secrets lie under the dust clouds raised by the deflection. Perhaps the terrain is unexpectedly fractured, or the crater is much larger than predicted. Each detail will find its way back into simulation models, refining them further. Over time, those refined models become the bedrock of credible planetary defense. If it all sounds like a grand experiment in cosmic risk management, that is precisely what it is. We are testing boundaries on a new frontier, one where our planet's well-being intersects with universal forces that have shaped worlds for eons. Asteroids in many ways define the history of our solar system. Now they are beginning to define the future as well. Each pass, each mission, each discovery lays another block in the foundation of an emerging discipline that might someday be as commonplace as weather forecasting. The difference is that this forecast deals with million-year cycles and the ephemeral moment when orbits align in perilous ways. Perhaps that is the ultimate gift these asteroids offer, a chance to confront our fragility and our promise, bound together on this tiny blue sphere. Where ancient civilizations saw dire portents in streaks of light, we see calls to action, an invitation to advance our science, unify our efforts, and push the boundaries of what is possible. That we have already managed to steer one small rock from its course is itself a testament to how far we have come. The journey continues, propelled by curiosity and necessity, toward an era where humankind takes its first steps in shaping the cosmic environment around us. It is an era that remains fraught with uncertainty. Even the best-laid plans can falter under the unpredictable nature of space. But each mission arms us with sharper insights, each blueprint grows more robust, and each success story fosters confidence that we can meet the challenge. The cosmos is indifferent to our hopes, yet we are not powerless within it. We stand at a crossroads between discovery and self-preservation, recognizing that the threads linking us to the distant orbits of ancient rocks can become entangled in ways that might change everything we know. In that realization lies both the greatest danger and the greatest opportunity humanity has ever faced. Subscribe to Frontiers of Infinity to explore more mysteries like this, because the universe is bigger than we can imagine. As more eyes turn to the sky, the simple question of whether an asteroid poses a tangible threat begins to reshape how we, as a species, view our place among the stars. What was once an abstract notion, ancient rocks drifting through space, now carries the weight of genuine stakes. Consider how quickly the news of even a modestly sized asteroid can grip the imagination. People read about its projected distance from Earth, debate whether that gap is reassuring or disconcertingly narrow, and wonder if there is anything ordinary citizens can do. In a sense, each publicized asteroid encounter becomes a lesson in cosmic humility. Those drawn to this realm of study often remark on the sense of unity it brings. Borders, politics, and daily disagreements fade in importance when confronted with the possibility of a planet-altering event. Some might think that talk of large-scale asteroid impacts belongs to distant millennia, yet the community of researchers, engineers, and policymakers who track these objects emphasize that long odds do not mean zero odds. A single outlier, a chunk of space debris that waltzes into the wrong orbit, could put us on a countdown few have seriously contemplated. This undercurrent of possibility is what fuels the quiet, relentless push to refine detection methods and potential countermeasures. Still, the conversation is not all about looming threats. There is an extraordinary sense of awe in the prospect of directly engaging with celestial neighbors. Missions to asteroids can reveal secrets about how the solar system began. Some scientists see these missions as modern-day caravels, venturing out to chart unknown territories. It is a chance to witness landscapes unaltered for eons, to observe craters and ridges formed in an era when planets were still coalescing. The combination of hazard and wonder proves compelling. One moment, an asteroid can stand as a destructive force. The next, a pristine time capsule from the system's infancy. These dual perspectives, danger and discovery, intersect whenever a new spacecraft slips free of Earth's pull, bound for an asteroid rendezvous. The data gleaned might transform our understanding of how collisions work on a micro level, how shock waves propagate through porous rock, or how grains of dust fuse in zero gravity. It might also show whether the attempts to shift an asteroid's orbit, undertaken in that first test collision, have ongoing after-effects we did not predict. Scientists keep an open mind to the possibility that altering one parameter can spark a cascade. For instance, if an asteroid's rotation speeds up, surface material might be flung off into space. Or if it slows down, certain regions might accumulate new layers of debris. Each result teaches us something about the complexities of these cosmic bodies. The potential for a man-made meteor shower, spawned by debris from that test collision, is a reminder that human interventions can echo across space in subtle but noticeable ways. While the likelihood of these fragments ever creating a light show visible to the naked eye remains uncertain, the mere concept has captured the attention of many. It illustrates a departure from the days when Earth was purely on the receiving end of celestial events. Now, in a small but consequential fashion, we have begun introducing changes. Whether that is cause for worry or celebration depends on one's outlook. Some see it as a testament to human ingenuity, others as a warning against overconfidence. The second probe, en route to examine the wreckage, promises to shed light on details we have only guessed at. Its small companion satellites will circle the asteroid, collecting data from vantage points that no Earthbound or even lunar-bound telescope could match. They may probe below the surface to see if the shock of impact opened fissures or rearranged internal structures. They could measure the precise distribution of mass, verifying whether certain theories hold true, like the idea that an asteroid might have a denser core hidden beneath a layer of rubble. The images and measurements will likely take shape over months, possibly years, of careful orbital maneuvers. Each pass yields a new snapshot, painting a fuller picture. In parallel, teams on Earth refine the software that predicts how future impacts might unfold. By inputting real-world data from the asteroid's changed orbit, they can see how closely it aligns with their models. If there are significant deviations, it means revisiting the equations that define momentum transfer, structural integrity, and debris dispersion. The result could be an updated algorithm that handles a wider range of asteroid types, making the next deflection attempt more precise. This iterative process, experiment, observe, adjust, stands at the heart of any scientific field, but the stakes here add an urgency unlike many others. There is also the question of how quickly these insights can translate into policy. Government agencies have begun drafting guidelines for what happens if a newly discovered asteroid is flagged as a collision candidate. When and how do they announce the threat to the public? Who leads the mission planning? Which nations provide the launch vehicles and which supply the payloads? Economic factors loom large, as building and launching a deflection spacecraft on short notice is a major undertaking. Some propose that the world should maintain a ready-to-launch system for planetary defense, similar to how certain rescue services are always on standby. Yet the cost would be substantial, and the political will to fund such a project consistently is not guaranteed. Meanwhile, private space companies also consider how they might contribute. Some see an opportunity to develop robust asteroid intercept capabilities, especially if, in the future, they plan to mine such bodies for resources. Others take a more cautious view, recognizing the liability that comes with intentionally moving large objects near Earth. If a company attempts to bring an asteroid into a stable orbit for industrial purposes and something goes awry, who bears responsibility for any risk posed to the planet? These questions reflect the evolving landscape of commercial space, where ambition runs high, but regulations and ethical frameworks are still evolving. On the broader cultural stage, each new development seeps into collective consciousness. Documentaries explore how a single space rock, if large enough, could alter Earth's environment for decades. They recount how similar events, millions of years ago, may have paved the way for mammalian dominance by eradicating the dinosaurs. The notion that another such event could happen tomorrow is jarring, even if the statistical probability remains low. Yet understanding that we have a means to prevent a modern extinction event, at least in principle, brings a cautious optimism that was absent from earlier eras. For many, the real surprise is how recently these breakthroughs occurred. It was only decades ago that astronomers confirmed what caused certain craters around the globe. Now, we talk openly of hitting asteroids with spacecraft and analyzing the results as though it were a standard scientific procedure. This rapid shift speaks to the accelerating pace of technology and knowledge transfer across fields. Rocketry, computer simulations, materials science, and planetary geology have converged to give us options our ancestors could never have imagined. Yet, behind every step forward lies the specter of potential miscalculation. What if, in an attempt to nudge an asteroid away from Earth, we inadvertently place it on a collision course with another body that matters to us, like a moon base or a future orbital habitat? What if a fragmentation event creates multiple hazards, some of which remain undetected until it is too late to respond? These scenarios might seem like contrived fiction, yet so did the notion of launching a probe to slam into an asteroid once upon a time. The line between fiction and possibility grows thinner as our reach expands. That expansion also shapes how humanity envisions its future in space. If mining asteroids becomes viable, we may begin redirecting small ones to orbits where harvesting them is easier. Some visionaries suggest building orbital stations that anchor to these rocks, using their mass for shielding against radiation. Others talk about carving out habitats within them. In such a reality, the difference between asteroid as threat and asteroid as resource becomes ever more blurred. The same stone that might strike Earth with cataclysmic force could provide materials to build the next generation of spacecraft or habitats. Learning to harness that duality is as much about diplomacy and ethics as it is about propulsion systems and spectrometers. Schools and universities around the world have picked up on the excitement, incorporating planetary defense and asteroid studies into curricula. Students simulate asteroid trajectories in computer labs, brainstorming novel ways to adjust orbits with minimal force. They analyze the data from prior missions, piece together the composition of these bodies, and debate the best strategies for dealing with hypothetical threats. The seeds of the next wave of innovators are thus planted, ensuring that asteroid research does not languish as a niche topic. Instead, it becomes a multidisciplinary arena where physics, engineering, biology, and even sociology collide. While these discussions evolve, the actual day-to-day monitoring of near-Earth objects continues, often quietly. Telescopes rake across the stars every clear night, logging faint points that move against the backdrop of the cosmos. Automated software flags anything unusual, prompting more detailed observations. In some cases, amateurs with backyard telescopes pitch in, confirming or challenging the coordinates. This global synergy of professionals and enthusiasts helps ensure that any newcomer to the region around Earth is noted promptly. Think of it as an early warning net stretching across the planet, knitted from countless lines of code and beams of light aimed skyward. And so the foundation grows, bit by bit. Each discovery, each passing asteroid, each new mission that returns data strengthens our collective preparedness. Yet the uncertainty remains. We cannot know if or when a sizable threat will materialize. Perhaps decades will pass without a crisis. Perhaps tomorrow, a small but not insignificant object will be found on a worrying trajectory. The best approach is to be ready for either scenario, to progress the science, refine the technology, and maintain open lines of communication among nations. The new probes, including the one now speeding toward the site of humanity's first deliberate asteroid strike, form the cutting edge of that readiness. When it arrives and begins its survey, we will gain a front-row seat to the aftermath of our species' decision to exert a cosmic influence, however small. The hum of transmissions carrying imagery and data back to Earth will be matched by the hum of analytical discussions in labs across the globe. And if the findings confirm the mission's success in shifting the asteroid's orbit while posing no serious risk to Earth, the technique may enter the mainstream of contingency planning. If the probe uncovers alarming complications, significant fragmentation, unforeseen orbit instabilities, then that reality will guide us to adopt new caution or develop improved techniques. In either case, we stand at a threshold. The space between Earth and the asteroids has grown just a bit smaller, not by physical distance, but by the scope of our engagement. Step by step, we are shedding the role of passive inhabitants and stepping into a new one. Custodians with the power to shield our planet or inadvertently escalate danger. It is a responsibility unlike any we have known before, simultaneously thrilling and daunting. One can imagine future generations looking back on these years as the era when everything changed, when humanity first tested the waters of altering another world's path. They might marvel at the primitive computer simulations of our time, or the relatively rudimentary rocketry we employed, and wonder how we ever managed. Or they might see this as the beginning of an unbroken chain of achievements, leading to a safer, more expansive presence in the solar system. Much will depend on how carefully and cooperatively we proceed. For now, the story continues with cautious optimism. The rocket that carried the probe away from Earth has done its job, and the craft sails through the quiet vacuum, propelled by a gentle burn of thrusters at key intervals. Mission control teams monitor its journey, ready to adjust course should any unforeseen obstacle arise. The small companion satellites rest dormant in their launch bays, awaiting the day they will deploy around the asteroid and function as roving observers. Astrophysicists on Earth refine predictions of what those satellites will find, each hoping the reality aligns with their painstaking calculations. All the while, new asteroids are being spotted, new orbital paths computed, and new questions raised about the role of humankind as both caretaker and user of space resources. Each piece of data, each theoretical model, each new detection method adds to a mosaic that underscores one essential truth. We live in a dynamic, cosmic environment. The orbits of celestial bodies can shift. The once lifeless void can surprise us with anything from a city-killer rock to a comet brimming with organic compounds. Preparing for any of these contingencies requires constant vigilance, a commitment to unraveling the mysteries of these drifting stones, and a willingness to step beyond the boundaries of Earth's cradle. Perhaps the most profound shift comes when we realize that the cosmos does not revolve around us, nor does it aim to harm us. Asteroids follow the laws of physics, not malice. Yet as sentient beings, we face the unique challenge of responding to their trajectories with intelligence and foresight. In this sense, the next sections of our journey will be as much about self-discovery as it is about mapping the solar system. We will learn how to wield knowledge responsibly, how to cooperate under the looming possibility of a global threat, and how to harness the wonders of space without losing our humility. That challenge, in the end, might be every bit as grand as the solar system itself. So we stand here now, with the echoes of a collision reverberating across light minutes of distance, awaiting the day when a second visitor will reveal the aftermath. We scrutinize new sightings in the sky, weigh the chances they might one day intersect Earth's path, and piece together strategies to ensure that if the worst transpires, we will have recourse beyond hope. Each incremental advance in planetary defense is a stride toward reclaiming a future once imperiled by random cosmic events. And in that act, unifying knowledge, technology, and will, we may find the seed of something extraordinary, a future where we protect not only ourselves, but the very tapestry of life that makes our world so precious in the cosmic dark. In these final moments of our journey, one cannot help but sense the tension between what is known and what remains to be discovered. Our instruments chart an asteroid's spin, shape, and composition, but the deeper truths, like whether it will become a future threat or a golden opportunity, lie in the delicate interplay of gravity, time, and human will. Mission planners and scientists alike concede that no matter how precise our calculations become, there will always be an element of unpredictability in the vast theater of space. What keeps them focused is the conviction that taking measured risks to learn, to adapt, and to experiment will lead us closer to a day when an asteroid menace can be turned aside with confidence. Even now, telescopes on dark mountaintops and satellites stationed far from city lights sweep the sky each night, tracing the faint glimmer of objects that might come our way. In computer labs and observation rooms, mathematicians model the gravitational whispers that guide these bodies, running simulations on supercomputers that mimic celestial dances over centuries. The data trickles in and reveals new insights, subtle shifts in orbit, unexpected brightness variations that imply tumbling motion or irregular surfaces, and rare chances to watch two asteroids pass near each other, shedding light on how collisions might transfer energy. Each observation is a puzzle piece, locking into a map we are still piecing together. Researchers notice trends over time. Smaller asteroids caught in Earth's vicinity tend to be ephemeral visitors, ricocheting through the inner solar system in looping arcs. Larger ones, discovered decades ago, are tracked carefully for any sign that their future passes might draw perilously close. Predictions reach far into the future, with many objects posing no immediate threat. Still, the cosmic environment is anything but static. A random nudge from Jupiter, a gentle push from solar radiation, or even a brush with another asteroid could alter an orbit, turning a benign spacefarer into a looming hazard. That possibility underpins the persistent push for better readiness. Readiness demands more than technology. It calls for a shift in mindset. Governments and agencies that once viewed space purely as a realm for scientific inquiry or national prestige are now asked to consider it a domain of planetary security. Funds allocated to research might one day translate into a deflection mission that spares millions from disaster. Citizens who tune in to news segments about potentially hazardous asteroids often discover that such designations are mostly cautionary. Yet the mere label provokes reflection on how fragile life can be when measured against the cosmic scale. In that reflection, people find common ground across nations and backgrounds. The threat of an asteroid does not favor any one country or region. It is an equalizer, reminding us that Earth itself is a shared sanctuary, vulnerable to forces beyond our normal control. This collective vulnerability can inspire unprecedented collaboration, as seen in joint missions and data-sharing endeavors. It is one thing to think about uniting for a scientific quest. It is another to recognize that the survival of entire societies could hinge on a carefully orchestrated space mission. There is power in that realization, a quiet determination that runs through the discourse of planetary defense. Another source of hope is the accelerating pace of discovery. The more eyes turn to the sky, the more digital tools deployed, the less likely it becomes that a sizable rock will slip by unnoticed. We are building a web of detection that grows denser each year, with automated alerts, cross-checked observations, and international databases. As that net tightens, the probability of a surprise impact diminishes further. Yet no one can guarantee absolute certainty. A small, fast-moving object coming from a sunward direction might evade detection until it is dangerously close. That slim margin of unpredictability fuels the call for space-based observatories placed strategically where Earth's own brightness does not obscure the view. Amid these cautionary tales lies a spirit of anticipation. We glimpse the day when we might have a catalogue of virtually every asteroid crossing Earth's path, complete with accurate orbits calculated centuries in advance. We imagine launching dedicated craft that can meet and gently steer any object straying too near. In the background, industries built around extracting resources from certain asteroids could finance better detection technology, achieving a kind of synergy between commerce and safety. It sounds ambitious, but so did the notion of landing on the moon once upon a time. As for that ongoing mission to the scene of our first deliberate asteroid impact, its progress serves as a kind of ticking clock. Each milestone passed in flight, each correction burn executed, draws it closer to the final destination. When it arrives, it will piece together the story of how a small spacecraft traveling at tremendous speed can change the destiny of a primordial rock. The data it sends will confirm or challenge our assumptions, revealing the full extent of the crater, the distribution of debris, and the ways in which the asteroid's orbit and rotation might have shifted. Should it find that the body has become more porous or fractured, we will know that a second strike in the future might produce multiple fragments. If it appears relatively intact, perhaps with only minor scarring, that outcome suggests our calculations of momentum transfer were remarkably on point. Those insights transcend academic curiosity. They become cornerstones of future preparedness. With each revision to our deflection models, we diminish the unknowns that could hamper a real emergency. That knowledge belongs not just to one agency or nation, it percolates into the collective consciousness of a civilization that may one day face a cosmic ultimatum. We do not know if that ultimatum will come in 10 years, 100, or 1,000,000. But history teaches us that major impacts have shaped Earth's past, and they will shape its future unless we learn to intervene. Small wonder, then, that a sense of solemn wonder attends the topic of asteroids. We tiptoe along the line between existential dread and cosmic opportunity. An asteroid might wipe out a city or deliver metals that spark a new industrial boom. It may harbor the secrets of the early solar system or herald the end of life as we know it. These extremes animate the imagination, reminding us that space exploration is not merely about pushing boundaries, it is also about safeguarding the planet we call home. And so we come to the finale of this chapter in our ever-evolving cosmic story. We began by looking at the silent wanderers in the sky, ancient messengers of both life and destruction. We traced the first test collision, celebrating the audacity of knocking an asteroid off course. We glimpsed the second mission racing through darkness to gather the truth of what that collision has wrought. And we explored the myriad ways asteroids continue to surprise us with their close passes and hidden complexities. Along the way, we confronted the delicate dance of knowledge, technology, and the sheer unpredictability of celestial mechanics. Yet the last word here is not fear, it is hope. Hope in the generations of scientists, students, and dreamers committed to pushing the boundaries of what is possible. Hope that a global community, drawn together by a shared desire to protect our delicate biosphere, can overcome differences when the stakes are universal. Hope that each new mission, each new nugget of data, each new policy framework is another step toward ensuring that humanity's story continues, unbroken, upon this blue gem in the cosmic ocean. While the night sky still holds mysteries beyond counting, we have proven that we can, in small but significant ways, shape our destiny against even the oldest forces of nature. So long as we maintain that resolve, marrying caution with curiosity, vigilance with vision, there is every reason to believe that we will face whatever the universe throws our way. And in so doing, we might just uncover wonders that renew our sense of awe, weaving hope and discovery into a tapestry that spans every corner of the solar system we share. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.